Well, welcome back, all 6 of you, the few, the proud. Okay, well, I have made a few corrections based on the compilation difficulties that do several things. It also makes it easier for people using Linux, 64-bit. What I've done, and if you can take a look at the screen there, I don't know if this is going to, is it visible? Shoot. Can you see the screen? Not really. Okay. Oh, shoot. How do I change that? I forget. Yeah, it's better. Let me change the font size. Okay, perfect. Sorry about this. I thought this was going to work, but I guess not. Okay. Okay, so I've got here, this is MATLAB R 2010A, but what you need to, if you're going to use the PCs in the lab, you'll need to use R 2010B. Not because A and B are so different, but because it's only B that they've connected the compiler to. Okay, done the installation for that. So the other thing that I've done is I've made it simpler now to nobody look at my password. I've made it simpler to use and install CSPARse if you're doing 32 bits. So, and I've posted it right here just last night. So use this, unless you've started already and you're working just fine for this project. Now, if you want to switch to this code, you're welcome to do it. You don't have to. But what I've done with this code is I've fixed the compilation. There's a problem with the compilation on the PC. But I also took the opportunity, I went ahead and since more and more of you are using 64-bit systems and the CSPAR is awkward to use, what I did is I changed CSPARse to this version 3. The int now is no longer an int, it's a new type called CSI for CSPARse integer. And this is now CSPARse 3, so if I look at the source, here, for instance, this is the code CS_compress that we looked at before. This is essentially identical to the CSPARse in the book, and it's also, and as such, it's different than CSPARse. CSPARse adds a lot of extra stuff that's kind of confusing. The only difference is that piece right there. So I have here a type called CSI, which is actually, even though it's all lowercase, I'm kind of breaking MATLAB, C rules. It's a pound define. And the reason I do that is so that at compile time you can redefine it if you wish. And it gets redefined in MATLAB. The integer in MATLAB is the pointer diff t, putter diff t. It's the integer that's the same size as an integer. It can hold any integer, any pointer difference between two pointers. So this is what MATLAB uses as its default integer. So all the integers inside a sparse matrix will be of this type. So this is 32 bits on a 32-bit system and 64 on a 64-bit. That's why I had to have that CSPARse, because ints didn't do it. Well, now I just change this so now by default in this C-sparse 3, this thing by default is pointer diff t. Okay. MATLAB has another name for this. They have a type def called MW signed index. They also, by the way, have something called MW index, which is actually the integer they use inside a sparse matrix. And this is unsigned because, hey, you know, you've got a row and column of a matrix, it's greater than equal to 0, right? It's not never negative. Well, I immediately typecast that to signed because the integers inside a sparse code very often need to be negative temporarily. Like a row index of -1 means I haven't computed the row yet, or there is no such row. Okay, so a negative number is used as a placeholder. It's also kind of awkward. Think about if you've got a back solve, say, and you have for I equals n minus 1, I greater than or equal to 0, I minus minus, do something, right? You're starting at n minus 1 and going to 0, and then you're going to stop. Well, now what's going to happen if I is unsigned? It's always positive, right? So this rather straightforward loop will break. So I don't like that. So I immediately typecast it from index to signed index. So unsigned integer to signed. But that works safely because the guys, I had this discussion at the MathWorks. We sat down together and said, this is not going to work. You're going to break all my codes. And he said, okay, we'll keep unsigned inside our codes because they like that inside other places. And then inside all the numerics, what they promised me was that they'll use unsigned integers, but they will promise me that the most significant bit will be 0. In other words, they won't use the whole range of the unsigned integer. That means you can take this and safely typecast it to signed, and you get the same value. Okay, so with 2's complement. So everything works fine. It's all great, except my laptop just turned off. So do use CSPARSE in 3 instead of CSPARSE 2.2.4 or CX-sparse. Okay. What I also want to show you here is, so here are all the C codes in the source directory. So these are the things. What you'll be doing is you'll be adding your files to the source directory, and then you'll also be adding, this is the MATLAB directory inside CSPARSE. You don't need to use this make file. In fact, you'd have to edit this to make it work on 64-bit system because you have to add a special flag, but instructions are there. So don't use that. Use this instead to install the package for the first time. Now, when you install it, you should save your MATLAB path. Okay, so you don't have to redefine your path every time. What you can do, if you do CS install, it'll add 2 entries to your path. If you type path tool somewhere down here, oh, I guess I haven't done it yet. Well, I need to change these. This is supposed to read CSPARSE MATLAB demo and CSPARSE MATLAB CSPARSE. Yes, that's repeated twice. So the CS install will do that, and then you need to use path tool or save path to save your path. If you're on a Windows PC, you can't save to the default location, so you need to save it into your MATLAB startup directory, which is normally documents/MATLAB. Okay, so if you just have a file called startup.m in there, or if you do save your path and it says where do you want to save it, I can't save it in the wrong place, save it to documents/MATLAB. It'll be a file called pathdef.m, and then you'll have to do that only once. So I haven't done that here because I can edit my path because it's my own laptop. So that's one thing about, and then when your cycle of edit, compile, okay, will be in here. These are all the MEX function wrappers. So if I edit, for instance, CS compress, I don't have compress. I think I have CS sparse MEX. So this is the MATLAB wrapper for that CS compress function, but it also does more things. It does the duplication removal, which I'll talk about today, and drops zeros and does a transpose. So I'm going to talk about these three methods, algorithms today, but I thought it'd be good to talk about the mechanics of CSPAR. So you see here again, all the MEX functions have the same header. They all look the same. Those first lines are always the same. It's always called MEX function, and it's always got 4 arguments. Period. Okay. What this function does, by the way, it takes this triplet form, these 3 arrays. It gets the number of elements here in T and Z, and then the column indices and the row indices, I use this CSMEX get int, which with this 1 flag here, it's going to subtract by 1. So I do the offset by 1 at this point. And if you came in late, you've got to watch the first 10 minutes. You'll be lost otherwise. And it's very important what I just said. So be sure to watch it on the tape. Anyway, so what you need to do to add your new code, you'll add a new MEX function to this directory and a new file to the source directory. And then to compile the code, there's a function called csmake. And right now it's compiling it because I guess it decided it wasn't yet. Yeah, it's not yet compiled. So it's compiling it. Oh, by the way, if you run this on the Linux machines in the department, every dot I print out is a compilation of 1 file. But what happens is every time the MEX command runs, it says, oh, did you know you don't have the right version of the GCC compiler, and this is only valid, 4.23 instead of 4.4, whatever. You get that warning every time, and there's no way of turning it off. The only way to turn it off is to ask the system guys to edit the script, which prints the warning, which they could do, but every time they install MATLAB, they got to edit that script, and it's a pain in the neck. So I might get them, if it's annoying to you enough if you use Linux, we could get them to fix that, because it's kind of nice to see the dots going across your screen and not have 30 error messages scream by. Now, one thing about the csmake is once it's compiled, it decides, oh, it doesn't have to be recompiled again, because it looks, the csmake is an M file, it's a MATLAB file, but it looks at the timestamps. It does like a Unix make. Okay. And then if you want to just make a particular if you want to make just a particular MEX function, see what it does, it says, well, if you change a source code, it doesn't know which source code depends, or which MEX function depends on which source code in the source directory. So if you touch any of the files in the source directory, it wants to recompile all the MEX functions. Sorry, that's the easiest thing I could think of. But if you know you only need to recompile one of them, you can just type this thing. For example, what if I only needed to recompile the CSPARS MEX function? Okay, it'll do that. So if I go over here to say this, and I'm going to do a trivial change, put a space at the end, and write it. Okay. Now if I type csmake, it'll compile that file, but then it'll compile all the MEX functions. Which, okay. If I just do this, it compiles 2 files and it's done. And all it did was compile the two files. So you got 2 dots there, ... So csmake now, ooh, that's ugly. Can you read that? That's the default colors? Oh, please. They got to be kidding. They really don't want you to read comments. There, is that better? Not much. That's a little better. Can you read that now? Okay. So within this csmake.m file are all the instructions for how to add your own codes. Okay. You can give this function, as I showed you, a parameter. You can give it csmake1 or some non-zero number, in which case it does a forced recompile of everything. Or you can just type csmake and then a single name. And MATLAB, by the way, has a very helpful syntax. If you call an M file or a MEX function, either way, with something like this, okay, with a string, parentheses, quote, string, parentheses, quote, okay. You can also do this. And it'll turn this into this for you at the command line. So basically, csmake and then your MEX function, and it goes. Anyway, so here we are, and to add a new function, there's like an 8-step process, but you only have to do it once per project. Okay. You create your source code file, csparse source cs mynewfunc.c, whatever. Optionally, you create a help file in the MATLAB directory. So, for example, cscompress.m. Whoops, where am I? Oh, it's called sparse.m. This is a wrapper. This is a helper M file, if you will. It doesn't actually do anything at all. What it does is, though, if you type help CSPARSE or help CSPARSE, I'm sorry, it'll print this information out. Everything up to all the comments here, up until the first non-comment line, which is this blank. So it won't print the copyright. If it tries to run a MATLAB function, okay, it first sees to say, oh, is there a cs_sparse MEX function that's compiled? Oh, okay, I'll run that. But if there's not, it'll look for the M file, which is this thing, which has nothing in it. And so that's right here. It'll print out, hey, it'll run this code, but then it'll say, hey, it doesn't exist. So this is useful, but not essential for your new MATLAB functions. Okay, you don't have to write this. Anyway, so let's go back to csmake.m. So you have to add the prototype of your source code to the include file, which I haven't shown you yet, but it's straightforward. You create the MEX function, and then you edit this file here to add the new function to two lists. So we've got two, and it's important that you stick with this naming convention here. CS mynewfunc_mex. Okay, what you're going to do is you're going to take this name right here and put it in not here, but in this list down here. So, for example, there's a MEX function called cs_add, which adds two sparse matrices together. And so you would have right here the name cs_add without the _mex.c. This is not strictly required in MATLAB to have the _mex, but that's what this file expects, the way it's constructed. That's just my convention. Okay, so it won't work if you have your MEX function named anything else but blah 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 _mex. You could get it to work, but you'd have to edit this file more severely. So all you have to do is add, your two, actually you're writing two MEX functions, add them both here, okay, but without the _mex, even though there's _mex in the C file name, okay. And then up here, all the files you add to the source directory, like for example, there's a source csadd.c file, okay, so it's listed there. There is, where's the compress we looked at? Here. There's the cs_compress that we just looked at, the .c file. There's no direct MEX function corresponding to this. There's a MEX function that combines several of these source codes together. So there's not a one-to-one correspondence. That's why you have to add it twice. And this was the fix. I added some fixes to make sure it could all run on 64 bits. So anyway, so this is optional. You don't have to do this. If you want to use the make file in Linux, Unix make, you can do step 7. Otherwise, just skip that. And then this is also optional. So steps 7 and 8 are completely optional. But this is steps 1 through 6 is what you need to do, and you only need to do that once per project. So it should now the system guys tested it on 1 or 2 PCs in the lab yesterday. I'm going to pester them to get it on all the PCs as soon as possible. You can use it, even if you normally use Windows and you like Windows. I feel sorry for you if you like Windows, but that's okay. You know, the more of you that use Windows, the fewer viruses I have on my Mac. Okay, because I'm less of a target. Right? Anyway, everything I just typed, everything I just did, my whole dialogue here. Actually, it's not so much a dialogue; it's more of a monologue because you're not talking back to me.
Do you want us to talk back?
Yeah. Well, wait. I have to repeat the question. No, I don't have to repeat. Do I have to repeat snide comments? Excuse me. Could I ask you guys in the back? No? Okay. I don't have to repeat snide comments. Please repeat all snide comments made. They will be rated. Everything I did on the Mac here will look just the same on Windows. It'll look just the same. It's all in MATLAB. It'll look the same on Windows. It'll look the same on Linux, on Mac, whatever. Okay. So let me do this CS install. This is, oops. You'll notice that you have to be in the right. By the way, you have to be, to run csmake.m, you have to be in this directory. You can't be in an other directory and then type it. It'll find it, it'll run it, and then it'll choke because it won't find the files in the right places. I could have gotten it to work otherwise, but it's a pain in the neck. And having a MATLAB file change directories in midstream is awkward because then if it dies in the middle, then you're in a new directory and you don't expect to be there. But anyway, so this is this CSPARS 3 MATLAB CSPARS directory, which is where all the MATLAB compiles are. What happened? I typed csmake.m. That's weird. Did it expect? Well, I don't know what it did there. Maybe it did this. It passed .m. I don't know what it did. Anyway, so here, the first time, and really the only time you have to do this is once, cs_install. It compiles all of CSPARS from scratch, and it shows you here that, oh, by the way, did you know you're running 64-bit? Yes, I do, but it's a nice reminder. In other words, my MATLAB function is checking to see, are you 32-bit or are you 64-bit? And it does things differently accordingly. So it's compiling the whole code, and then it's going to run a little demo, but it's also going to fix up my path, which fortunately right at the moment is broken. It's not pointing to the right place. So I'll show you the new stuff it'll put there, those two lines. So while that's compiling, fortunately you don't have to, and now it's going to run this big fun demo, and it's going to run a bunch of the code. Not all the codes. It's not going to run all the codes. There is an exhaustive test directory. There's a CSPARS MATLAB test, and if you go in there and type test all, it'll run for about 20. You tried it, I think, but it didn't work because it requires on the CXSparse it thinks it's complex and it doesn't work on Windows. But this will work on Windows. This is the demo, though. This is just running a quick demo of some of the main functionality. It's not exhaustively testing it. Okay, so and then when that's done, we're on page 14 of the textbook. this is an interesting little test. It's comparing 4 different methods of creating a sparse matrix. And as you can tell, some of the methods are a lot, and this is the runtime it took for the 4 different methods, and you can tell some methods are a lot better than others. Okay, so there's a command called path tool, or you can go up here and where is it? You know, I don't remember where to find it. I've closed all of the toolbars. I don't have all my fancy toolbars up here just to keep it simple. But there is a place. Works correctly with the command history command window. Where is it? I can forget. There's a place you can click a button to get this thing path tool. But anyway, I'll forget that for the moment. So it actually put three things in my path. Okay, it put in CSPARS 3, MATLAB, UFGet, the demo, and CSPARS. Now UFGet is kind of handy, and I'll show you in a minute what that does. That provides a simple MATLAB interface to the entire University of Florida sparse matrix collection, about 18 gigabytes worth of sparse matrices. Okay. And what will happen is you can, but I have my own UFGet down here somewhere. Yeah, already installed. So I want to move this to the, you don't have to do what I just did. In fact, let me pretend I didn't do that. Let me move this back down. So this is what you will see. You'll see these 3 new directories. And you just want to save this. And now it'll save that for your next session. But if you're on Windows, on the lab machine, it'll say, oh, I'm sorry, you don't have permission to write to the system directory. It'll ask you, do you want to save it somewhere else? Yes, you say, and save it to your document/MATLAB directory, which is where MATLAB starts up. And then you're good to go. You don't have to do this anymore. Just do it once. And there's 3 files here. This is where the CSPARS directory, MATLAB/CSPARS is where all the MEX functions are. The demo directory is where all those demos were that you just saw. The UFGet directory is something altogether different. And what it does, it's a function which downloads a problem from the sparse matrix collection. If you just type UFGet by itself, it prints for you a listing of all the matrices in the collection. I just printed out almost 2,400 of them. Okay. You can describe a matrix by name, which you don't know all the names of the matrices. Okay. It downloads the thing, and it has a MATLAB. This is called a MATLAB struct. So it's a struct object, and it's got all these different components. So, for example, prob.title, which is a string, and it's got prob.a. And there's a thing in MATLAB called SPY, but I have something better in CSPARS called CSPY for color spy. And where is it? Oh, they put it here in my existing figure. And it does a color plot of the matrix, where the color represents the absolute value of the entry. It's kind of prettier anyway. It's easier. It kind of helps to understand the numerical values. There is it makes for some handy ways of testing your codes. You can say for example, index equals UFGet, and you get this struct with all these different components for the directory. Okay. And help UFGet. It makes for a handy way of running examples. For example, type UFGet example. Here's a little example which all it does is runs all the symmetric non-binary matrices in increasing order of number of rows in the matrix. Okay, so it loads the index, It uses MATLAB to find those matrices which have numerical symmetry and are not binary. It sorts that list by the number of rows in the matrix, so smaller matrices will load faster anyway. And then it goes through the loop, prints out the name, loads it, gets it, displays the problem, spies it with a title, and shows you the web page, and then asks you to continue. So let's type this, UFGet example. UFGet is a part of CSPARse. It's inside CSPARse, if you will. It's actually a separate, completely separate unit. But UFGet example will download these matrices, and one by one, it'll show you there's the web page for the matrix. It'll show you, where's the SPY? Did it spy it or did it C-spy it? Oh, it spied it. It didn't C-spy it because I don't assume. It's hard, you know, if there's a little button on the MATLAB desktop. You can dock a window. This is kind of cool. See that little arrow? You click that, and suddenly now it's inside. It's a window inside your. So this is looking at a web page. This is a web browser. And it pulled up the first matrix, and so I hit continue, and then it'll show me my next, it'll show me my next one. And there's the matrix, and it spied it here. Let me dock this one as well. Figures, no. Let's see, how do I want to tile. Let's see, how do I tile? Shoot. Well, anyway, so it's plotting, it's drawing a picture of the matrix, and it's also showing you the web page for the matrix, which has got more pictures in it. Whoops! And if you click on the picture, you can go to Yifan Hu's website at AT&T. He's the one who. This is a graph that was automatically generated for the matrix, and we're just going to, it'll just cycle through all these different matrices one at a time. And there's the matrix, and there's its graph. And this makes for a nice way to pull up some test matrices for your problems. Now, there's other ways of generating test matrices for your exercises. Let me terminate this and close these. You notice, by the way, it downloaded all of these. Okay, but if you run this code again, it didn't download it because it already had. It's cached. It'll cache all 18 gigabytes. Where's my command window? Oh, whoops, over here. All right, whatever. It didn't download it. It just loaded it directly because I already had a copy of it downloaded. Now, what this means, if you go hog wild and want to look at all the matrices, you're going to have 18 gigabytes worth of data on your machine. So you'll probably run out of space unless you've got on your own system. You may run out of space on the departmental system. If you're on the departmental system, you could edit UFGet to point it to the actual location for the matrices. You don't have to download them at all. They're just mounted on the remote file server. I could show you how to do that if you want to. But when you turn in your projects, what I'm going to have you do is going to tar up or zip up your entire CSPARse 3 directory. But UFGet is a part of this. Where am I? Oh yeah, MATLAB. It's in the MATLAB directory, UFGet. So here's all the these are subdirectories of where all those different matrices were put. This directory will get 18 gigabytes in size, so you don't want to submit the whole thing, even though it's a component of CSPARse 3. Okay. So when you submit your projects, please temporarily, remove. In fact, you might do this permanently. Remove this UFGet directory elsewhere. Put it in your documents /MATLAB directory or wherever you wish. and then edit the path accordingly so that, you know, change this path up at the top where it says where the UF-get is. Because don't turn in an 18 gigabyte zip file, please. You'll have a hard time doing that. Okay. So that should, I think, get you up to speed in, yeah.
Just real quick, how to edit UF-get to point at the sources?
Oh, yeah. There is a, let's see. Oh, to point at, let's see, UF-get defaults, I think. Where am I? Oh, VI. You saw what I just did there. You know what I use now. UF-get defaults, and it's got it sets a params.dir for your local directory for downloaded MAT files. Okay. Don't change the URL because that's, you know, that's where my files are on the web. Okay. Let's see, top tier. Top. You can also edit a file called ufsettings.txt. Let's see. I don't have instructions on how to do that. You need to change this top tier, I think. You need to edit this file to point to well, in Linux land, it'd be like this: CIC/sparse/public HTML CSC research sparse. CSC research sparse/public HTML. And I think, and that's the directory containing mat, mm, and rb. Yes, I think that should do it. So if you edit this file right here, but this is the path from Linux and Unix land. I don't know what the path is from Windows land, how to mount that remotely. CIC research sparse public HTML, and that's where the, because if you go there, you can't see this. Yeah. So yes, it's CIC research sparse public HTML. It's you're basically directly connecting to the location where all the files are on the web page, all 18 gigabytes worth. Then they will have to be downloaded. Okay. Well, that's a lot of mechanics, I know. And for those of you who are not here, I hope you listen to it on the tape. But just to recap, use the new CSPARS 3. It'll be easier than using CXSparse. And it'll also actually work on the PC, where the CSPARS 2.2.4 doesn't work with the compiler. Even if they install the compiler, it doesn't work on Windows. And if you're using Linux and you have everything working fine, go ahead and continue using that. But you might find the CSPARS 3 simpler. And for Project 2, I'd ask you to start with the CSPARS 3 so that everyone has the same base to start with. So it's a little more easier to grade and work with you on those different pieces. Okay, those are a bunch of mechanics. Now I'd like to get to back to the more algorithmic kind of stuff. Okay, we left off, we looked at the transpose, and we looked at the, no, we didn't do this. Did we do the transpose? No. We left off, what's that? Yeah, we left off looking at the conversion of the triplet to the compressed column and the cumulative sum. the cumulative sum function is very simple. It just computes the cumulative sum of those vectors and returns them. So I won't belabor that point. It's pretty trivial. Although you notice even in a trivial function like this, I check to make sure that my caller didn't run out of memory. So if my inputs are null, that means my caller tried to allocate them and failed, and so I return an error message that says, hey, I don't have my inputs. It's little things like that that make a code more robust to memory errors and things like that. So now I want to show you the transpose. So this is a function which transposes a matrix. Now if you look at this and compare it, if you have your textbook in front of you and compare it with the cum sum function, it's almost identical. Because what the transpose function is doing, okay, the way you can think about it is it's just a bucket sort. We have a matrix A, and I want to compute C equals A transpose. Okay. Now, one way to understand that is to say, well, I'm not actually doing a transpose. I'm making a copy of the matrix, but putting it from column form into row form. And so I have these different rows of the matrix here. Row 0, 1, row 1, row 2, and so forth. So what I want to put in here are column indices, and of course the numerical value. And what I have here are the columns 0, 1, and 2, and what I have in here are row indices. And so building this looks just like you're building a compressed row matrix instead of compressed column matrix, but is it row or is it, this is where it actually helps to be dyslexic. Because it doesn't really matter, is it a compressed row matrix or is it a compressed column matrix of the transpose? Well, it's both. So if your brain can oscillate really quickly between the two, it's actually true. It's the truth, So being dyslexic is actually beneficial here because it actually reveals the actual truth of what's going on. It's both at the same time. So what we had to do in the triplet case was we had to scan through all the triplets. We had to count up how many entries are there in each column, so I know how big to make these buckets. And then I went through a second pass and filled the buckets. Well, now I need to go through these indices first, but don't count how many entries are in each column, because I already know that. I want to count how many entries are in each row, because that is going to define how big each of the row buckets are. Yeah? Yes.
Why can't it be done in place?
Oh, the question is, why can't it be done in place? It's possible. It's very difficult to do because the data structure rearranges quite erratically. It's possible, but it's very painful. I could explain an algorithm for doing that if you like. It can be done. It's extremely irregular memory access, actually. It's worse than even this one. And that makes it a lot slower. And you have to do things like, okay, I have to move this entry to the right position, but the position that it's supposed to go in is taken by another entry that's in the original matrix, not the transpose matrix. So if I'm going to move this here, okay, now, but to do that I have to first move this one here. But this is somebody's still in the right. Well, but then I have to move. You get these long chains of dependencies, which you can follow, you can do. Okay, but it's very painful to do. So I just make a copy. So what has to happen then here is in the code, I go through, yes, and you're right, I allocate a matrix. Now, fortunately, I know how big it is. It's A and Z, which is right here. So allocate, I spallic a matrix, sparse allocate, the matrix C. And I allocate a workspace of size M, because I'm going to have M rows here. M rows of the compressed row matrix. It's then M columns of the compressed column matrix. Okay. You notice that the spallic has this reversed. It's not M rows and N columns. It's N rows and M columns. But I'm now thinking it in terms of compressed row because it's easier. If I think about it in terms of transpose, my brain will electrocute. So then I go through and do the row counts. How many entries are there in each row? So to do that, we don't actually have to walk through column by column. Oh, look at the count in the first, count in the second, count in the third. I can just iterate through the entire row index vector without regard to what column they're in. So it's a single for loop. Then, just like as before with the triplet, there's a cumulative sum. And then, as before with the triplet, these two loops were just one loop. Loop through all the triplets and put them in the right place. Well, now I just have to loop through the columns because now I need to know what column it is in. Loop through the columns, then loop through every row in the column, and then that gives me now the row index I right here, AI of P, and the column index J. And so if you're at a column J and you see a row index I, then you go to row I and put J in its right position. So that's what's happening here. J is put in the right position. Now there's a very interesting side effect, and I've got 4 minutes so I can explain this. There's a really terrific side effect of this function. This is a bucket sort. It sorts the entries. Because think about what's happening. I go to column 0. Okay, suppose I've got indices in 1, 5, and 10. Row indices 1, 5, and 10. So what's going to happen is I'm going to put a 0 in rows 1, in rows 5, in 10. I'll put a 0 index in those rows. Now I'll go to column 1. Suppose I've got, and this could be out of order. Whatever order this was in, I'm going to do the same thing. 1, 5, and 10. Suppose this is 5, 1, and 12, and 13. So it's out of order. So I'm going to go to row 5 and put a 1. And then I'll go to row 1 and put a 1. And then I'll go to 12 and 13 and so forth. But see, look what's happening here. This row, I'm inserting the first column and then the second column and then the third because I'm going through the columns in order. So as a result, all of these rows will be sorted. It's a bucket sort, that's all. It's a bucket sort. The triplet form to the compressed column form is not a bucket sort because the triplets are not visited in order of an increasing column index, but these are. So the transpose acts as a sort. Duplicates is a whole other topic, and that I'll have to. Let's see how much time I got. 2 minutes left. So duplicates is the next slide. Okay. Now, if to handle duplicates, okay, that's what I'll have to talk about next class. But imagine you have so now the question is, you've got a compressed sparse column matrix, let's say. So we know how to transpose. That's easy. This transpose also does a sort. That's helpful. We could use that to exploit to get rid of duplicates, because if I have a duplicate now, the duplicates would be placed next to each other. That's convenient. So that would be one way of getting rid of duplicates, is to sort the matrix first and then go through and prune, and you find the duplicates are adjacent, so you can then prune them out. That's one method of doing it. It'd be linear time, but it requires the transpose first. You can actually get rid of duplicates without doing this transpose. Suppose you're in column 3 and there's a row index 5, and down here there's a row index 5, and here's a 2 and a 2 and so forth, and a 1 and a 3. Okay, and you want to produce a matrix that looks like 5, 2, 3, and 1. You want to add these two entries together. You want to add those two entries together. Now let's suppose I wanted to do this in place without making a copy. Think about how you would do that. Any ideas or suggestions? How you would go through the matrix and do this for every column? What would you do? In place. You're not going to not create a copy. Think about what you would.
Mark it with a special character.
What's that?
Mark the duplicates with a special character and then
mark them.
You have to scan it twice.
You scan it twice, but then you have to, you can mark it as a duplicate. How do you know it's a duplicate? And not only you have to know what it's a duplicate, where it's a duplicate, but you have to know where its pair is. Or there could be 3 places where it's duplicate. Okay. Think about it. I mean, you can cheat and read the book, of course. But how should this be done efficiently? And I'll show you a way that can be done you can do it in linear time. One solution would just be to sort this first, either with a transpose, well, that makes a copy, or sort it with an n log n kind of in-place algorithm. That gets the logarithmic factor in there. We don't want to do that. I'm going to show you how to avoid both of those on Friday. So we'll stop here, and I'll see you then.